Students, welcome to Sunil's tutorial. I'm Sunil Nirwani and today we'll be doing this chapter called as wave motion. First of all, let's define what is a wave. How do I define a wave? Right? A wave is defined as an oscillatory disturbance traveling through a medium without change in form. I'll explain this to you. Definition. First, let's write the definition down. It is defined as an oscillatory disturbance traveling through a medium without change in form. Right? That means if I speak, as I speak, or when any sound is produced, that creates an oscillatory disturbance. If the same oscillatory disturbance travels through without any change in form, then that is called as wave. Fine, do we get this thing here? Now, in order for propagation of wave to take place, so that sound moves from one place to another, that's called as propagation of wave to take place, a medium is required. Now, what kind of medium is required, or what are the properties that a medium should possess so that wave can travel from one place to another place? Let's see this. I can say that propagation of wave motion can take place only in the medium which have the following properties. First, in order for propagation of wave to take place, the first property that the medium should possess is elasticity. Unless and until the medium is elastic, propagation of wave will not take place, because particles of medium must have a tendency to return back to their original position after being displaced. Only then propagation of wave will take place. Right? Second, inertia. Right? What is inertia? The medium must have inertia, that is the capacity to store energy and transfer it in the form of waves. That is the second property required for propagation of wave. Third,
in the second part
this medium should have inertia. Why should it have inertia? So that if it has inertia, it will have capacity to store energy. As I speak, there is an energy that is produced, and that energy has to be then transferred in the form of wave. So unless and until the particles do not have inertia, they will not be able to transfer the energy in the form of waves. Right? Next, the third thing is little frictional resistance. The third property is that they should have very little frictional resistance so as to avoid loss of energy during wave motion. The particles are going to be propagated from one place to another. If they are going to be propagated, there has to be least resistance so that maximum energy can be transferred from one place to another. Right? Now, in the case of a wave, let us try to understand. Suppose if this is a wave, let's consider a transverse wave. This is the maximum displacement of the wave from its mean position. The maximum displacement of the wave from its mean position is called as amplitude. Right? The time taken by the wave to complete one full motion is called as the time period. Right? The number of such waves that you can get in 1 second is called as frequency. Right? So let's write the basic definitions down. Amplitude. For a wave, let's try to define what are the parameters. The maximum displacement of any particle on either side from its mean position is called amplitude. Right, that is what is amplitude. That's the maximum displacement of the particle from mean position. Next, period. What do we understand by period of the wave? Period of the wave is the time taken for a particle to complete one full vibration. That is starting from here, going up, going down and reaching the point again. Right? So the time taken for any particle to complete one vibration is called periodic time. Right? Next, frequency. What is frequency? How many such vibrations can be performed in 1 second is called as frequency. The number of vibrations performed per second. Number of vibrations performed per second is frequency by any particle. Is called frequency. Fine, do we get this thing here? Now, frequency is represented either as N or it is represented as F. Both the symbols are for frequency. Now, since I can say that periodic time one oscillation is completed. Time oscillation. In periodic time T, one oscillation is completed. So in 1 second, how many oscillations will be completed? In 1 second, x will be nothing but 1 upon t. But number of vibrations per second is nothing but frequency. Therefore, I can say that frequency is 1 upon t. Thus, frequency is going to be nothing but 1 upon time period. Right? Do we get this thing here? Next, what do we understand by wavelength? Suppose if this is the wave, the distance between two consecutive crests or two consecutive troughs is called as wavelength. The distance between two consecutive crests or crest or trough. Crest is the upper part, right? The distance between two consecutive crests or two consecutive troughs is called as wavelength, right? Or in short, I can say that wavelength is the distance between two particles which are in the same phase of vibration, right? Or I could also say that wavelength is the distance between two successive particles which have a phase difference of 2 pi, right? Or I could say that wavelength is the distance traveled by the wave in one period. So you have multiple definitions for wavelength. Fine. You could write any one of them, all of them are correct. Wavelength. Wavelength is nothing but the distance traveled by the wave. The distance traveled by the wave. Wavelength is nothing but the distance traveled by the wave in one time period. Fine, do we get this thing here? So that is called as wavelength. Next, let's see what do we mean by velocity. Velocity. What is velocity? Velocity is the distance traveled by the wave per second. Velocity by normal definition is the distance traveled by the wave in 1 second. Distance traveled by the wave in 1 second, right? Or per unit time is called as velocity. So by definition we can say that velocity is nothing but distance upon time. So I can therefore say that velocity I'm going to represent as v. Distance traveled by the wave is lambda, that is my wavelength. Time is t, right? So therefore I get v is equal to lambda by t. So I can say that v is equal to lambda into 1 upon t. But we know that 1 upon t is nothing but frequency. Therefore you get v is equal to n lambda if I substitute. So that's the relationship between velocity, frequency and wavelength, right? Velocity is nothing but frequency into wavelength. And do we get this thing here? Next, what do we understand by phase? Right? Phase of vibrating particle indicates the state of vibration that the particle is at a particular instant. What is the angle that it has covered? Right? So phase is nothing but phase of vibrating particle. Phase of vibrating particle indicates the state of vibration of the particle. State of vibration of the particle. State of vibration of the particle at that instant.
So I understand.
Yeah, I'll just explain to you. Still. Suppose if this is the wave, right? Now this is 0, this is 90 degrees, this is 180 degree, this is 270 degree, this is 360 degree. If a particle is vibrating, it is going to cover some angle, right? So at a particular instant, what is the angle that has been covered by it? At a particular instant, what is the angle covered by it? That would be the phase of vibration. Fine, do we get this?
Which angle?
See, at any, in order to reach this much distance, or in order to cover this angle, it has to cover some distance. So if it covers some distance, in terms of UCM, it is going to cover some angle. The basic concept of UCM, guys. Suppose if a particle is at A and it moves at B and comes back, it is an oscillatory motion. If it moves from A to B, it is going to cover some angle at the center. That angle that is going to be covered is called as the phase. Right? Do you understand what is phase? Okay. Once I know what is phase, then I can say what is phase difference. Phase difference. Now, phase difference, as the wave propagates through the medium, different particles of the medium are disturbed at different instants of time. So when two particles of the medium are in different states of vibration, then a phase difference is said to exist between them. So what is phase difference? It is the difference between the state of vibration of two particles. Right? One particle has covered an angle of 30 degree, the other particle has covered an angle of 45 degree. What's the phase difference between them? 15 degrees. They are in different states of vibration. Right? So what is phase difference? As wave propagates through a medium, different particles of the medium are disturbed at different instants of time. Right? Now, when two particles in the medium are in different states of vibration, when two particles in a medium are in different states of vibration, then a phase difference is said to exist between them. Then phase difference exists between them. That is phase difference. Next, what do we mean by angular velocity? What do we understand by angular velocity? Angular velocity, the rate of change of angular displacement of the particle with time is called as angular velocity. Velocity is nothing but distance upon time. If the body is covering an angular distance, the angular distance covered by the body per unit time would be its angular velocity. So this is nothing but the rate of change of angular displacement, the rate of change of angular displacement of any particle with time, is its angular velocity. Right? It is represented as omega. That's how you write angular velocity. Finally, get this thing clear. Now, let's try to understand that. Let's try to get this in one time period. In one time period, the particle returns back to its original state of vibration. That means one full wave is completed. In one time period, the particle returns to its original state of vibration. In simple language, it completes one wave, original state of vibration. Right? So in that case, in one time period, what is the phase that is covered by it? In one time period, it covers a phase of 2 pi radians, because if it is going to get back to its original position, it has completed one full circular motion, so it is going to cover a phase of 2 pi radians. Therefore, the change in phase per unit time, change in phase per unit time. What will be the change in phase per unit time? It will be nothing but 2 pi upon t. T is the time period of the wave. Thus, and change in angular displacement per unit time is nothing but angular velocity. Thus, angular velocity is nothing but 2 pi upon t. Fine. Next, what do you understand by wave number? Wave number is nothing but it is the reciprocal of wavelength, right? Not reciprocal of wavelength, yeah, it is the reciprocal of wavelength. Wave number is nothing but the reciprocal of wavelength. The number of waves in unit length is called as wave number. The number of waves in unit length is equal to wave number. Right? It is equal to wave number is reciprocal of wavelength. Find the way of this thing here. Next, what do we understand by particle velocity? What is particle velocity? The instantaneous velocity of a particle in a medium executing a simple harmonic motion while traveling through the medium is called as its particle velocity. As the particle moves, this is a wave. At any instant as it moves, it's performing simple harmonic motion because it's going to complete the first wave and then get back to its original position, right? it's going to be a repetitive type of motion, therefore it's performing simple harmonic motion. Now at any point of time, the particle executing SHM when traveling through a medium has some velocity, and that's called as the particle velocity. The instantaneous velocity of a particle executing SHM traveling through the medium is called as its particle velocity. Right? So what is particle velocity? Particle velocity, it is the instantaneous velocity of the particle. It is the instantaneous velocity of the particle of the medium executing SHM when the wave is simple harmonic motion, when the wave is traveling through the medium. When the wave is traveling through the medium. Fine, do you get this thing here? Now let's try to get an equation for an SHM, right? Or let's try to get an equation for the wave. Let's find simple harmonic progressive waves. Simple harmonic progressive wave equation. Try to see a wave traveling through medium. This is a wave traveling through the medium. Its maximum amplitude is plus A, its minimum amplitude is minus A. So it is oscillating between minus A and plus A. This is my origin. X-axis, it's moving with a velocity of v in the direction of x-axis. Let's assume that it has covered a distance of, at point P, it has covered a distance of x on the x-axis, and it has covered a distance of y on the y-axis. Right? So, let's try to form an equation for this. I can say that simple harmonic progressive wave traveling through the medium do not reach simultaneously for all the particles. One particle will vibrate as I speak. One particle will vibrate. It will complete its oscillation, will transfer the energy to the adjoining particle, will transfer the energy to the adjoining particle, and that's the way the energy is going to be transferred. So all the particles are not going to reach all the particles do not reach simultaneously, right? Traveling through the medium do not reach simultaneously. I can say that simple harmonic progressive wave. Simple harmonic progressive wave traveling through a medium. Traveling through a medium do not reach simultaneously. To all the particles. Right? Hence, the particle does not start to vibrate. Hence, all particles do not start to vibrate simultaneously. While this particle is vibrating, the particle which is close to you is not vibrating. So I can say that all the particles do not start vibrating simultaneously and are not in the same phase. Right? Hence, all the particles vibrating simultaneously. Hence, all the particles do not start vibrating simultaneously and are not in the same phase. In the same phase, right? Each particle starts vibrating a little later than the preceding particle till the time the energy reaches, and this lateness increases from particle to particle as the wave moves. However, it should be noted that all particles vibrate with the same amplitude and the same frequency, right? So I can say that each particle starts vibrating a little later than the preceding particle. Each particle starts vibrating a little later than the preceding particle, and this difference increases from particle to particle along the wave. This difference increases from along the wave. So thus now we know that all the particles are not vibrating simultaneously and there is going to be a time lag. So what we are going to do is we are just going to consider one particle. So consider the case of a simple progressive wave which starts from origin O and is moving along positive direction x-axis, traveling with a velocity of v, right? Let's assume that y indicates the displacement of a particle, where the particle has covered a distance of x along x-axis. Fine. So let's just write this basic assumption down. Consider a simple harmonic progressive wave originating at O and traveling in positive direction x-axis along with velocity v. Traveling in positive x-axis with velocity v. Let us assume that y represents the displacement of the particle. Y represents the displacement of the particle. Let's assume that y represents the displacement of the particle and x represents the position in the medium. And x represents the position in the medium. Right? So you have both the values. Now as the wave proceeds, each successive particle in the medium will be set into simple harmonic motion. First particle will complete harmonic motion, next particle, and this will go on. Now at time t is equal to 0, the particle is going to be at the origin, right? Now the displacement y of particle at a given position can be given by the formula of simple harmonic motion. Simple harmonic motion displacement is y will be equal to a sin omega t. That's the displacement along x-axis, right? I can say as the wave proceeds, each successive particle in the medium is set into SHM. Each successive particle of the medium is set in SHM, right? Now at time t is equal to 0, at time t is equal to 0, the particle at origin passes through the mean position. The particle at origin passes through mean position. It passes through mean position. Now, as it passes through mean position, the displacement y of the particle at O, the displacement y, at O at time t can be given by is y is equal to a sin omega t. From where did I get this equation? This is my equation of displacement of SHM, right? But omega we had derived was 2 pi upon t. We have derived omega is nothing but 2 pi upon t. So I can say y is equal to a sin 2 pi upon t into t, right? Now, where a is the amplitude, a is amplitude, omega is angular velocity or angular frequency, and t is the time period. So I have the basic equation ready.
So both
right?
the t's are time.
Excuse me?
Both the t's are time.
This is the time taken to reach point P, and the capital T is the time taken to complete one full wave. Okay. Now, this was when the particle reaches O, right? Now, let's assume that let P be the particle in the medium which is at a distance of x from O. Let P be a particle in the medium at a distance of x from O, right? Now, as the wave travels with constant speed in the medium, the time taken by the wave to reach V, time taken by wave to reach P, time is nothing but distance upon velocity, will be nothing but distance is x, velocity is v, so that will be the time taken. That means that the particle will start vibrating after x upon v time. The time difference between the two particles of vibration, one which is at origin, one which is at P, is going to be x upon v. So I can say that particle at P will start vibrating x upon v time later, than the particle at O. Right? After x upon v time, first particle at O will start vibrating, and it will take x upon v time for the particle at P to start vibrating. Therefore, I can say that the phase lag between them is going to be x upon v. That is going to be the time difference between the two particles. Therefore, I can say that the phase lag in time between the two particles is x upon v, right? So therefore the displacement of particle P at time t will be the same as the displacement of particle at point O. The only difference is that it will be after time interval t. The particle at point O will have a displacement of y. The particle at point P will also have a same displacement of y. What is the difference between them? That particular displacement at particle P will take place after time x upon v, right? So I can say that.
So it will be written as t plus x upon v.
I'm coming to that. That's what I'm just giving the theory for, right? So I can say that the displacement of the particle at P, displacement of particle at p at time t will be the same as the displacement of particle at point O, right? At same as the displacement of particle at point O at a time x upon v earlier. The particle at point O had the same displacement at a time interval of x upon v earlier. So the particle at point O had the same displacement at t minus x upon v, right? That is right. Hence the displacement at particle p at time t can be substituted. Displacement of particle at t at time t. I can substitute this. How will I substitute this? I can say that I have the equation for an SHM, except that now the time interval is going to be t minus x upon v. So I'll get y is equal to a sine 2 pi by t, and instead of t I will write t minus x upon v. Fine, do we get this thing here? So this is going to be my equation for displacement of particle at any time interval t, right? This represents the displacement of particle t at time t. This represents the displacement of p at time t. This is how much is going to be the displacement. Okay. Now let's try to represent this in different form. So my general form equation for displacement is y is equal to a sine 2 pi by t minus x upon v. And why do we have that equation? We just wrote the entire theory on that. Particle at point O will have some displacement, particle at point P will also have the same displacement, but it will have that displacement after time interval of t by v. So by the time it reaches point O, that much time would have elapsed, so I have to subtract that time of x by v, and that's the reason why you have time interval as t minus x by v. Okay, now let's try to represent this equation in different forms. I can say that, but we know that 1 upon t is frequency. Therefore, one form of representing this equation will be a sine 2 pi n t minus x by v. I'm going to represent this equation in multiple forms and show it to you, right? But we know that 2 pi n is equal to omega. 2 pi n is nothing but omega. So I can say y is equal to a sine omega t minus x by v, right? Now I can say that let's consider the equation. You can say again y is equal to a sine 2 pi n t minus x by v. If I consider this equation, let's take the n inside. If I take the n inside, I'll get y is equal to a sine 2 pi nt minus xn by v. I could represent this, but n by v, but n upon v is nothing but lambda. Therefore, I could say that n upon v is not lambda, n upon v is 1 upon lambda, right? N upon v can be written as 1 upon lambda. So therefore I could say that y is equal to a sine nt minus x upon lambda.
2 pi.
2 pi I forgot to write, minus 2 pi nt minus x upon lambda. I could represent the equation in this way also, right? N can be written as 1 upon t. So I can say y is equal to a sine 2 pi t upon t minus x upon lambda. Same equation represented, right? Now I could say that we know that n is equal to v upon lambda. Substitute n as v upon lambda in the original equation. I can say again y is equal to a sine 2 pi n t minus x by v. N can be substituted as v upon lambda, but n is equal to v upon lambda. Therefore y is equal to a sine 2 pi v upon lambda t minus x by v, right? So this can be written as, take this v inside, so in that case I will get y is equal to a sine 2 pi by lambda vt minus x, because v and v would get cancelled. So in that case, if I take that 2 pi by lambda inside, so I'll get y is equal to a sine 2 pi vt by lambda minus 2 pi x by lambda, right? Now 2 pi v by lambda is nothing but 2 pi v by lambda. V by lambda can be written as nothing but n, so which is nothing but 2 pi n, and 2 pi n is nothing but omega. So 2 pi v by lambda can be written as omega. Therefore y is equal to a sine omega t minus 2 pi x by lambda, right? So this can be written as 2 pi x by lambda can be written as, out of which 2 pi and lambda are constant, so I can say y is equal to a sine omega t minus kx, right? Where I'm assuming where k is equal to 2 pi upon lambda, right, which is called as the wave constant or the propagation constant. Fine, do we get this thing clear? So these are the different ways of representing the same equation. The same equation can be represented in multiple ways, right? Now, I could also say, instead of taking minus, I could say that if the wave is traveling in negative direction x-axis, if the wave is traveling in negative direction x-axis, that means the point which is there on negative direction x-axis would have experienced the vibration before the same vibration is experienced by the point at origin. Therefore I can say that y in that case will be nothing but a sine 2 pi by t plus x by v. There we had t minus x by v, here you will have t plus x by v. So in negative direction x-axis it will be y is equal to a sine 2 pi t by t minus plus x by v. Right? Do we get this thing here? So these are the different ways in which a progressive wave can be represented. Okay, we'll stop this here for the day. Thank you very much.